What we want to go over right now is the sequence of operation on a heat pump and cooling. It's going to have the same preconditions for operation as anything else. High voltage, low voltage, fuses, all that stuff has to be good. The sequence is really similar to a standard air conditioner and cooling. So the thermostat has an integral time delay. Then it's not going to start for 2 to 5 minutes, generally a 5-minute time delay. 24 volts is set from R on the thermostat to Y, G, and O on the thermostat. Y is sent to power. Y sends power to the defrost circuit board. 24 volts is sent through the refrigerant low pressure switch and high pressure switch if equipped. Contacts closed, sending power to the outdoor fan motor and the compressor. G sends 24 volts to the indoor fan relay. The indoor fan relay coil is energized. Contacts closed, delivering power to the indoor fan blower. O sends 24 volts to the defrost circuit board. 24 volts is sent to the reversing valve. From the defrost control, the reversing valve coil is energized, switching the reversing valve to cooling mode. Outdoor contactors, 20 system runs in cooling until the temperature drops to thermostat set point. 24 volts is then no longer sent through Y and G on the thermostat. The outdoor contactor coil is de-energized. The indoor fan relay is de-energized. And generally, 24 volts will remain on O until the thermostat is switched out of cooling mode to off or heat mode. So we can take a look at the typical heat pump control schematic. Look at the air handler first again. Here we have all the abbreviations used for all the different components. There's a bit more than there is with just an AC, but all of them are there so that you can see what everything's labeled, what that means. So on the air handler, we have HR, which is the heater relay. So that's going to power the electric heaters. We have the FR fan relay, which is going to power the fan. Now notice on this air handler that we have a normally closed set of contacts on the fan relay. So this is going to be a single pole double throw relay with a normally open and normally closed set of contacts. This ensures that if the heat is powered, but for some reason the fan is not calling to run, then power will automatically be sent to the fan anytime those heaters are energized. It is very important if you replace a indoor fan control board in an air handler or this fan relay that you put one that has a similar configuration so that you don't run the possibility of running the heater without the fan running. Unfortunately, this won't do anything to protect it if the fan motor is not working, but that's what your high limit right here and your fusible link right here is for. Sometimes it's equipped with both, sometimes it's only equipped with one of them. But either way, these will open if the heaters begin to overheat. Notice the high limit is just a temperature switch that's in the normally closed position. As the temperature rises, it opens. The fusible link is generally a piece of metal made to melt at a particular temperature, and once that breaks, the heater has to be replaced, or the fusible link has to be replaced. Have our indoor fan motor here, which is of the same design as in our other air handler. Transformer, fan relay coil, here to relay coil, wires out to thermostat. Oh, and the heater element right there. So the thermostat is a little bit different on a heat pump. Now, granted, most electronic thermostats can be set for conventional or heat pump, but either way, the internal workings when that thermostat is set to heat pump is going to be a little bit different than if it's set to conventional. So notice we have the same fan auto on switch, same auto off switch, same heat cool selector. We also have a heat or emergency heat selector, and that's going to dictate whether or not the outdoor unit runs in heat or if you only power the emergency heaters. If we set the thermostat to cool, then you can see that it's going to automatically power the O wire, the wire going to O, which is going to keep the reversing valve powered until you switch operation. We have a cooling thermostat for cooling, a heating thermostat for heating, and then you're going to have an additional thermostat essentially inside of that thermostat, which is going to, once you get far enough away from set point, it's going to power the auxiliary or emergency heat if it's not set in emergency heat. So after a particular amount of time or a particular amount of difference from set point, electric heat will come on to bring the temperature closer to set point and that'll continue until the thermostat reaches set point, and then that process will repeat. Heat will come on the outdoor unit after a set amount of time or deviance from set point. Then the auxiliary heat will come on, and then both will stay on until the thermostat is satisfied. So basically, you have essentially 2 extra thermostats inside the thermostat, 2 extra temperature switches, and you're going to have the extra selector to switch between heat and emergency heat. The condensing unit similarly has a few more components. So we have a circuit board for defrost, and we're going to go into the defrost process in a different sequence of operations. Just understand this whole thing is here essentially so that this unit can switch to defrost and heating if necessary, because anytime you're below about 45 degrees outside, there's a possibility that the condensing unit is going to freeze up, and or the outdoor unit is going to freeze up, and we're going to have to switch that unit into defrost to melt the ice and then continue a heating operation. For now, all that is happening with the defrost board is we're getting R in. It's going to power the defrost board. It will need R and C because it needs to be powered. It's going to go into a logic circuit, which is basically all there to control defrost operation. The low pressure and high pressure switches, if it's equipped with a high pressure switch, which we're showing here, low pressure switch, normally closed switch, opens on a fall of pressure. High pressure switch, normally closed, opens on a rise in pressure. Normally these travel through the defrost board, but the defrost board doesn't actually monitor their operation. It's basically just terminals in and out so that you can use the connections at the board to monitor whether or not these switches are open and closed. But unlike a furnace circuit board, it's not going to tell you if those switches open or closed. There's generally not going to be an LED or anything like that that's going to light up if it's not operating because the low pressure switch isn't operating. The reason that's important is because sometimes a defrost board will be condemned when it's the low pressure switch that's open. So obviously always check your charge and always check the position of that pressure switch, whether it's closed or open, before you say, well, the board's not working. After it goes through the low pressure switch and high pressure switch goes back to the board, that wire is going to continue out to the contactor coil, which powers the outdoor contactor. W goes through a relay into the board because it will actually power W in defrost. O goes through the circuit board and then down to the reversing valve, and that has an extra power source to it so that the defrost board can power the reversing valve if necessary when initiating defrost, which is always necessary if you have an O terminal. If you have a B terminal, it would be the opposite. But this whole schematic is based on having an O terminal, not a B terminal. B terminals, of course, energize the reversing valve in heating, not in cooling. And then we have common because we need power. Defrost thermostat is here, which is a normally open switch that closes on a fall. Generally, it's going to close at 35 degrees, open at 55 to 65 degrees. And then the rest of it is same to a typical condensing unit. We have our compressor, internal overloads, outdoor fan motor, dual run capacitor, and contactor contacts. Now we can take a look at the schematic when it's actually powered. On this one, I don't actually show the connections between the units on the thermostat wire, but obviously all these terminals labeled the same will be connected with wires that are going to the same terminals between each one. So starting at the thermostat, R is sent from the air handler, the low voltage side of the transformer, to R on the thermostat. Power is going to come in, go through the auto off switch, go through the heat cool switch, come down, power O through the heat cool switch, continue, go through our cooling thermostat, and on to our outdoor unit, Y. And then G is going to be powered through the fan auto on switch to our air handler. G comes over to the air handler, powers the fan relay. That closes the fan relay set of contacts, opening the other contact that is on the heater switch. So this set of contacts opens, this set of contacts closes. That sends power to whatever speed you have selected on your multi-speed blower, if it is multi-speed. Otherwise, it powers your terminal there. L1 is always powering the other side of the indoor fan motor. In this schematic, if you had a double pole set of contacts, that set of contacts would also be closed from the fan relay. In the condensing unit, R is powering the outdoor circuit board. Y is going through the low pressure switch, through the high pressure switch, over to the contactor coil that closes these contacts, powering the compressor and the outdoor fan motor. Notice on the outdoor fan motor, we come down through a set of contacts. There's a relay on the defrost board that powers the outdoor fan motor, and this would open in a defrost mode. But anyway, it goes through that set of contacts, powers the outdoor fan motor. We see O comes through, goes over, and that's powering the reversing valve, putting it in the cooling position. And that is the extent of a heat pump sequence of operation in cooling.